Limits at infinity. So up until now, we've been plugging in limits at specific integer values or at specific constants. But now we're going to take limits at infinity. So here's what you should probably write down if you don't have it in your notes already. Okay, for limits at infinity, what we're really talking about, let's visualize it like on a graph. If I have the graph of y equals 1 over x, let's say, it's going to look like this. It is the divorce graph. So when I say find the limit as x approaches infinity of this graph, let's call it y, we're saying for very, very large values of x, what is the value, the y value approaching? And as you can see, as we get closer and closer, further to the right, the height of the graph is approaching 0 because we have this asymptote here. Similarly, if I were to do this on the left side, as x approaches negative infinity, so as I'm going, my x values are getting further and further to the left, the graph is also approaching 0, but from the underside, right? It's a negative. It's almost like a 0 minus. But that's what we're talking about when I say limits at infinity. We don't care about the middle of the graph. We only care about the far left and the far right, where x is approaching infinity. So another term I want you to think about when we're describing limits is horizontal asymptote. That's what we're looking for. So in general, finding limits at infinity, we get numbers like this. That's a very, very small number. It's approaching 0. So when the denominator grows faster, then our answer will just be 0. Now, in some instances, we'll have the same degree on the top and the bottom. Here I have a 5x squared. So the 2 here is the highest power. So I'm focused on this leading term. And in the denominator, the highest power is actually the second term, negative 2x squared. Since they have the same exponent, I'm going to rewrite it. Notice that the x squareds will cancel, and my final answer is negative 5 over 2. Now let's say there was a cubed on top, then we wouldn't even be looking at the 5 or the 2 at all. We would just say the numerator is growing faster because the degree is higher. The answer would be infinity. If the denominator had a 5 there, though, then the denominator would be growing faster, so the answer would just be 0. Okay, and so that's limits at infinity in a nutshell. Let's try this problem. So we need the horizontal asymptote, which just means, right, the limit as x approaches infinity. Actually, both positive and negative infinity will be, well, let's observe the highest degree on top. When I multiply this out, I would get 2x squared on top. And when I multiply this out, the highest term won't be the 6 here. It will be the negative 9x squared. So that's what I want to focus on. 2x squared and the negative 9x squared. We have, notice, the same degree, so we'll take the ratio of the leading coefficients. So this would simply be negative 2 over 9. Let's show our work a little bit more thoroughly. We can say this is approximately 2x squared over negative 9x squared, because as we discussed last time, the other terms like the 6 are just so small they don't even matter. And then we'll show that these guys cancel. Answer is negative 2 over 9. Okay, let's try the same. This one is explicitly asking for the limit, but it would be the same if it said find the horizontal asymptote. It's just a limit at infinity. So let's get the highest degree on top. The leading degree on top would be, well, when we square this, we would get a positive 4x squared. And in the denominator, the leading degree is the 1 here, so we have 3x. Now notice, if I were to cancel my x's, I'm left with an x on top, meaning that as x approaches infinity, the top is growing much, much faster. So this would become infinity, is my answer. Or you could say does not exist. Right? There is no asymptote, after all, if it's growing forever. So either of these answers is acceptable. Let's try another one. Again, we're looking for the leading term. So careful here, we have to multiply 2 times 2x. But if we distributed it further, we would also multiply with the x here for a leading term of 4x squared. 2 times 2x is 4x, times x is 4x squared. Notice I'm not even bothering multiplying this 2 with the negative 5. It already has a lower degree, so it's going to be one of those terms that cancels. That ultimately doesn't matter. So we're multiplying this guy and this guy. Now on the bottom, if I were to cube this, I would get x times x times x, which is x cubed, plus some other stuff, right? But there's also a 3 in front. So in the denominator, my leading term would be 3x cubed. Notice upon canceling, we're left with an x in the denominator. That means the bottom is going to be growing as x approaches infinity. So our final answer will be 0. So look at the difference between number 10 and number 11. We got almost the same thing, 4 over 3. The only difference was the x was in top, so our answer was infinity, versus the x being on the bottom, in which case our answer was 0. It's all about where the higher degree is. So I urge you to go back and copy these down. Okay, try this problem yourself. Pause the video and give it a shot. So on top, my leading coefficient is 2x squared. On the bottom, my leading coefficient is negative 4x squared. Since these are identical, they both cancel, leaving me with an answer of negative 1/2. Let's try 13 together. Again, I'm looking for leading coefficients. That'll give me 2x squared on top. On the bottom, very carefully, I'm noticing that if I were to multiply 3 minus x times 3 minus x, my highest degree term would be a positive x squared, plus some other stuff. And then I also have to be concerned with this 2x plus 5. So my leading term at the end of the day would be x squared times 2x, which is 2x cubed. Upon canceling, I see I have an x left in the denominator, and actually the 2's go away as well. So this really starts to look like the 1 over x curve for really, really large values of x. But at the end of the day, the limit then is 0. Okay, now we're no longer dealing with rationals, which are fractions, and polynomials, like we were before, right? Everything we've done so far has had some sort of polynomial on top and a polynomial on the bottom. But now I'm just seeing an exponential curve. So it's important here to know what your exponential graphs look like. Y equals e to the x. Notice it's a growth curve. It's going to look like this, with a horizontal asymptote at 0. Now, if you know that and you know how to transform these, then these are pretty straightforward. Let's discuss our graph. First, I'm going to rewrite it so that the e to the x term is in front, and we'll add the 9 at the end. This is like standard form. Okay, so notice we do have our exponential growth curve, because the base is greater than 1, right? E is 2.7. So it's going to grow, but because there's a negative in front, it'll actually flip the curve down. I also know that if I add a constant at the end, that it's going to shift my graph, in this case, up 9 units. So it's shifting up 9 units. So my horizontal asymptote now has changed. From being y equals 0, it's now y equals 9. Now, here's the only thing that sets these apart, these types of problems, apart from the fraction problems we were just doing. Notice that the horizontal asymptote only really applies for negative infinity in this graph. Because at large values of x on the right side, the graph's actually going down forever. It's not approaching the asymptote in the same way that it is on the left side. So we have to write two separate equations. So we would say the limit as x is approaching negative infinity for f of x equals 9. That's the left limit. But the limit as x approaches positive infinity, in this case, doesn't exist. There is no limit on the right side because it's negative infinity, right? There's no limit at all, aka it's going down forever. So if they asked us about the limits for this problem, we'd have to answer with two separate limits. The only time where you have the same limit for both that you can comfortably count on is when you have the fraction problems. But coming back, notice they actually asked us for the horizontal asymptote, which, if you know the definition, is just y equals 9, because we follow this format, y equals a times b to the x plus c. Whenever we have an exponential function, that plus c is our horizontal asymptote. So we could have actually just answered with 1. But keep in mind the distinction. If they asked for the limits at infinity or at negative infinity, we would have to say that one side is 9, the other side has no limit. Okay, let's try 15. Probably this is a little complicated for the exam, but just in case, they have been creeping up the difficulty level each year. I would say this is for any students interested, plan on getting a 5. Let's try this problem. It says find the horizontal asymptote here. So again, we don't know how our graph behaves when we have exponentials involved. So we're going to take the left limit and the right limit separately. Okay, actually I'm going to write the whole thing because we'll plug in and see what happens. Notice actually that our variable is not x, it's a. So I'll go and write as a approaches infinity and as a approaches negative infinity. Okay, let's start with the top first. Because we have a fraction here, we can't think about our regular asymptotes like that plus c, as we did in the last problem. So for this one, we're just going to have to plug in negative infinity and see what happens. 2 minus e to the negative infinity all over 4 plus e to the negative infinity. Now, what happens when I take e to the negative infinity? Let's see what happens. I have 1 over e to the infinity. E to the infinity is going to become some hugely large number, right? It essentially becomes infinity itself. I have some number that's bigger than 1. In this case, it's like approximately 3. Multiplying it by itself infinite number of times. So this will become 1 over infinity. And 1 over an infinitely large number becomes approximately 0. So this entire expression, based on the logic right here, became 0. So let's plug that in. We got 2 minus 0. Using the same logic, the denominator becomes 4 plus e to the negative infinity, which also is 0. So our final answer is 1/2. That's our left side limit as a approaches negative infinity. Now let's see what happens when on the right side as a approaches positive infinity. We'll plug it in as before. So 2 minus e to the positive infinity over 4 plus e to the positive infinity. Keep in mind that as e is getting larger and larger, right, that's e to the infinity power, that 2 there is not going to play any role. So we're essentially left with negative infinity. But that sign matters, right? Because negative infinity is different from positive infinity. On the bottom, as e becomes infinitely large, that 4, the fact that we're adding a 4 isn't going to make any difference. So we're canceling it out. and focusing on the leading terms. Now we have negative infinity over positive infinity, so that leaves us with a negative 1, right? These are the same, so they'll cancel out, leaving us with a negative 1 over 1. And so this is a very unique problem. Don't stress over it, but if you were able to follow the